Alright, we continue with the capsule videos from KEYTER Academy discussing the basic components of the heat pump, and today we are going to talk about the thermostatic expansion valve. The generic expansion valve performs an expansion of subcooled liquids from this liquid that is in the completely liquid zone, 100%, and passes them inside the bell to a mixture of liquid vapor with a percentage of each of them called quality. Within the expansion valve, it plays a crucial role in establishing the boundary between high pressure and low pressure. And ultimately, what it will do is precisely determine the flow rate of refrigerant circulating within the refrigeration system. It will obviously be positioned between the condenser and the evaporator. The valve types we have are the thermostatic expansion valve, which is the one we'll be working with today, and the electronic expansion valves. The thermostatic expansion valve is slow in operation, as it operates with a range of pressures and a temperature, resulting in a regulation and modulation that is not completely fast. When working with inverter equipment, with equipment that has to comply with eco-design regulations, that modulation has to be faster, so we work with electronic expansion valves. The components of the thermostatic expansion valve include a diaphragm, which is the central control unit that operates based on a range of pressures to regulate the opening and closing of the valve using an adjustable spring. An adjustment screw, which will determine the maximum opening that the expansion valve will have. A needle, which will transmit a force from the diaphragm to the expansion valve itself, which is a needle valve, can be either closed or open, thereby controlling the refrigerant flow from the condenser to the evaporator and regulating the cooling process of the system. The bulb, which will be filled with the same refrigerant that the expansion valve works with and will transmit, depending on the temperature it detects. Now we will see where will transmit a pressure through the capillary to the diaphragm, okay? The adjustment screw, as we have mentioned, sets the maximum opening of the expansion valve. That diaphragm will determine which pressure prevails. Now we will witness and ascertain what the pressures are. The needle, which will transmit force to the valve, bulb, and external balancer, ensures that if the expansion valve is connected to an evaporator coil or plate heat exchanger with a very high pressure drop, this drop may falsify the temperature measured by the bulb and the pressure it transmits. In other words, the external balancer serves as a check to determine which bulb is telling the truth by compensating for the potential inaccuracies caused by the high pressure drop. The needle's role is crucial in maintaining accurate measurements and ensuring the reliability of the system's readings. The operation of the thermostatic expansion valve is based on the pressures of the evaporator transmitted through here, the bulb pressure transmitted through the capillary tube, and the adjustable spring pressure, which, as we have mentioned, depends on the adjustment screw and remains constant. The primary missions of the valve are to regulate the flow that passes through it, thereby controlling the power of the equipment, and also ensuring proper superheating for the equipment to operate without the compressor absorbing liquids, thus preventing potential damage and maintaining optimal performance. If we are not completely in the superheated vapor zone, but instead we are suctioning liquid plus vapor, that liquid will damage the compressor, causing a liquid blow, so we must avoid it at all costs. Our objective is to regulate the operation of the equipment and ensure safety by preventing overheating. Overheating occurs when there is a temperature difference between the gas drawn in by the compressor and the saturated vapor temperature at the evaporation pressure. If this temperature is too low, we are taking a significant risk. We could find ourselves in a situation where the valve is unable to respond quickly to a change in load, causing the compressor to draw in liquid, which we know can be deadly for the compressor. Therefore, it is crucial to carefully monitor and control the temperature to avoid such hazards. Therefore, this overheating must be within certain preset values, because we also do not want to have long overheating periods, as it would mean that the battery is undersized and also that the compressor discharges high temperatures when unloading, which is also not desirable due to oil issues. To control this superheating, we have the bulb at the discharge of the evaporator rather than at the compressor suction. All the piping leading to the compressor acts as an additional superheating, a safety superheating. Therefore, if we place the bulb at the discharge of the evaporator, we will be on the safe side because we will have a kind of extra superheating, 1 degree, that we will achieve in this connection tube towards the compressor, and then the equalizer that will be close to the bulb to check what we have mentioned, that the bulb is telling the truth. How does it work? Well, in the diaphragm, 3 pressures come together. We have a constant spring pressure determined by the valve drill, an evaporator pressure that increases and combines with the spring pressure to determine which of these when added to the bulb pressure, overcomes the other. This interaction between the pressures is crucial in understanding the functioning of the system. The bulb pressure will be determined by the temperature of the refrigerant gas in that bulb at the discharge of the evaporator. In the event that you experience a high temperature, it indicates that your pressure will be high. In the event that you experience a low temperature, it indicates that your pressure will be low, thereby determining the proximity to the dew point. If the pressure of the bulb is higher than the combined pressure of the spring and the evaporator, it signifies that we have a high temperature at the bulb. This high temperature results in the transmission of a high pressure, indicating that we are far away from the dew point line. Hence, our course of action is to slightly open the valve due to having a battery that is too small, an evaporator with a long superheat, enabling greater refrigerant flow, and a slight reduction in superheat. This ensures that we remain within the desired range and make full use of the entire evaporator. Currently, there is a section of the high evaporator that is superheating refrigerant unnecessarily, rendering it useless. Conversely, if the bulb pressure is less than the sum of the spring pressure plus the evaporation pressure, it indicates that we are in close proximity to the dew line. The temperature recorded by the bulb is low, transmitting a low pressure, and we find ourselves in a precarious situation where we could potentially surpass the dew line and the compressor may initiate the intake of liquids from the evaporator. Thus, our course of action is to close the expansion valve because we currently have an underpowered evaporator. We need to reduce the flow of refrigerant to ensure that the superheat progresses properly and the refrigeration cycle operates efficiently. The valve is not completely open or completely closed, but it possesses modulation. As we have mentioned, it has a gradual modulation, but it modulates within the limits established by the manufacturer. When we have a small superheat, the valve, for example, in this case is 5 degrees, the valve will be completely closed. Why? Because we have an underpowered evaporator, we need to increase its superheat, which means we have to decrease the refrigerant flow rate. If we have a very long superheat, it means we have an extended superheat, an overpowered battery, so the valve will open to allow more refrigerant to pass through, giving more power to the entire equipment, and also to reduce the superheat a bit, because it is useless to overheat, so it will always be working on this ramp based on the sum of pressures we have seen. Well, that is all, and we will see you in the next video. Regards. Thank you for watching, and stay tuned for more informative content in our upcoming videos.